Okay, in this question we are asked what is the pH of a 0.420 molar solution of this thing called C5H5NHBr, and you're given a Kb, an ionization constant for this base, C5H5N, and it has a value of 1.7 times 10 to the minus 9th. Okay, so a little bit of discussion before we actually launch into the solution. And this will be of interest to those of you who have to take organic chemistry in the future, that this C5H5N is really a weak base. It's an organic weak base. Each one of these corners represents a carbon atom with a hydrogen atom branching off from it, and these double lines represent double bonds, and it has a nitrogen in it. And you will learn in organic chemistry that a lot of nitrogen containing organic molecules are weak bases, and this is just one of them. Its name is pyridine. This is a weak base called pyridine, so it's a weak base. So what do weak bases do? Well, they accept H+, they accept protons. So when this thing acts like a weak base, it takes on an H+, and it becomes this ammonium-like salt. I say ammonium-like because it really does the same thing that ammonia does. It adds the hydrogen, giving a formal charge of +1 on the nitrogen. And so we could represent that with the C5H5NH+. Okay, and so that is the positive ion that is going on in this salt, where we have the pyridine that's been protonated for the positive ion, and a bromine as the counter ion, a negative ion. Now, that's going to get kind of messy and complicated, so what we're going to do for the rest of this solution is we're just going to say that this is B. Okay, we're going to call that base B. And so when I put a hydrogen on it, I'm going to call this the conjugate acid, BH+. Okay, so this is the weak base and this is the conjugate acid. And so I'll use that notation for now in the rest of the solution. All right, so we have a salt that has one of its component ions being related to a weak acid or weak base. And this one right here, the BH+, is related to a weak base. So the conclusion to that is that it will react with water. Okay, so it will lead to a non-neutral aqueous solution. So now I'm going to show you how to figure out the pH of that solution that has this compound dissolved in it. All right, so this is a conjugate acid, so it's going to do what conjugate acids do. So this BH+ is going to find a water molecule. Okay, so that's aqueous. Water is liquid. It's going to do this in a reversible way, and it's going to give that H+ to the H2O to form hydronium ion, aqueous. And what is left behind is just the bare base, and that is also aqueous. All right, so this becomes the heading of our RICE table. All these kind of problems where we're asked to calculate a pH of a weak acid or weak base, and we're given an ionization constant, and we're given an initial concentration. These are RICE table problems. So I'm just setting up my RICE table here. Each one of these compounds is going to get a column. Okay, and as always, I'm just going to ignore what the water does because it is not included in the equilibrium expression. And I know that my initial concentration for this BH+ is 0.420. Okay, because that's the molarity of my salt. So whatever concentration I have of the salt, I'm going to have the same concentration of BH, and in this case I'm going to have the same concentration of bromine. All right. Now the other thing I'll point out is that this number is underlined because in the problem set that you have, it may be a different number than 0.42, but the solution will be the same. You'll just use a different number here in that block. Okay, and so again, this is a pre-equilibrium concentration, so these concentrations are 0. All right, and so the reaction is going to shift to the right because we don't have any products yet, so we're going to gain X amount of each of these products at the expense of this reactant, so we'll lose X amount of that. So we bring our columns down, 0.420 minus X, X, and X, and then we